In this video, we show the practices that support ongoing changes in student thinking. We show 3 days of activity in which Anna introduces new ideas through direct instruction, has students use those ideas to reason about an experiment with the melting of ice, then has students add to the public record of knowledge that we have referred to as a summary table. Anna then engages her students in a second investigation to help them reason more deeply about the molecular basis of evaporation.
So this is just showing kind of how ice is stuck together water molecules. So all these molecules are packed in, they're moving just a little bit, but they can't really move out of that space. And this would be like an ice cube. See how it's in the shape of a cube? Yeah. It's just this really tightly packed structure. If what we're talking about is true, that the only way that a solid melts is by other molecules hitting its molecules and making them move far enough that they can overcome their attraction, kind of like we were talking about how the attraction matters. Then, if this is an ice cube, is it going to melt from the inside out or from the outside in? What do you think? Where will those molecules be able to turn into a liquid first? So this would be the inside, and that would be the outside. So today we're going to do a lab, and our goal is going to be able to not just describe what the ice is like and what the liquid is like, but also to describe what happens to make that change. Okay, so we're going to be talking about heat transfers again. So we're going to explore what is actually happening with when ice melts by comparing the way ice melts when it's surrounded by air and the way it melts when it's surrounded by water. So our question is, does it melt faster in air or water? And then of course we're going to explain why down at the bottom. Okay, but for now I want you to think, if we put an ice cube in air or water, then the ice cube will melt faster. So you make a decision. Is it going to melt faster when it's surrounded by air or when it's surrounded by water? And then I want you to try to explain why you're thinking that. So just so you know, the air in the room is our air, so it's room temperature. And the water we're going to use is from this pitcher, and it's been sitting out all of lunch, so it's also room temperature. So I'm going to give you 2 minutes, and I'd just like you to write your very first ideas. Doesn't matter at all if a prediction turns out to be wrong. I just want you to document your original ideas, record your ideas. In your 2 cups, you will have one person bring these cups up to the cooler. This is where the ice is. I've tried to make sure that all the ice cubes are the same size, but make sure you pick out 2 that are the same size. Put 1 in each cup. So everything will look the same at first. Once you have your ice cubes in the cup, then you come over to me. I will be standing here pouring water into one of the cups. Then you're ready to... Sorry?
Can you drink the water?
No, don't drink this water. Then you're ready to bring it back where you will place the cups inside the bin. That's where they will stay the rest of class. These cups should not be outside of the bin. So where will the cups stay?
In the bin.
Tell me what's in one cup.
Ice. One ice cube.
Okay, and then if we have one ice cube in this cup, what's in the other cup? Ice and water. All right.
What do you mean ice cubes melting in the cup? I'll zoom in on it.
And the cup with water, it's melting quicker.
But not in the other cup, huh?
Yeah.
What the heck is happening there?
Because that one's cheating.
That one's chilly and that one's not?
No, that one's cheating.
Oh, that one's cheating? How is it cheating?
Because it has water.
How is that cheating?
Just this.
Why? Cameron, what do you think? Why is it cheating? Why is it cheating to put water in one?
Because it changes it.
Yeah, that melts faster than that. It's just sitting there.
What?
But why?
What, doing? You got a problem here?
Yeah, I got problems.
Because
water,
you.
it's like it's faster to melt something.
But why?
Because it's like this.
You said it was moving around.
Liquid
Yeah, all right, let's talk about molecules.
Like it's more water molecules and stick.
Then ice just sitting there.
Liquid makes ice melt faster than ice just sitting there, and Curtis is going to bring it to molecules. You just were talking about molecules.
Yeah, it's like sticking the molecules from the ice cube and like shifting into the water.
It's shifting molecules from the ice to the water, and that's why it's melting faster?
Yeah, and that one, it doesn't have like the liquid, so it takes longer.
So how do you think it's shifting the molecules? Like what?
Like they're moving, and then the molecules from the ice cube are going into the water.
How are they moving in?
Slowly.
Like, but why do they do that?
Because the molecules
Like-
attract one another.
Like why? Oh, the molecules are attracted to one another. But why are they more attracted to the water than to the ice? That's a hard question.
Because the ice, it's water, but just frozen. Is that one melted faster? I know why now.
Why?
Because you put in this one, there's no heat in it, and this one, the water is the same temperature as the air, but
There's no heat in this one? There's
but
zero
not that much.
heat?
There is, but
Must
not,
be cold.
Not that much.
Oh, not that much?
Yeah, but in this one, you put the heat in the cup. This one, they're going in, but slowly.
What do you guys think about that idea? There's more heat in the water cup than there is in the air cup.
Oh, the ice is starting to make the water colder.
But it's starting to make water in the air cup too, right? Like it's a little bit melting in the air cup?
You melted a lot.
Well, what's the difference between the heat in the water cup and the heat in the air cup?
Because you put the heat, the water heat directly into the cup, but in this one you don't. The heats are going inside it, but slowly.
All right, so Raul's making a claim.
The heat molecules in this one went in the cup faster than they went into this cup. Because I don't know.
What do you?
The molecules in the water are connecting to the molecules from the ice.
Okay. So you guys are missing out because Elizabeth is the only one talking about molecules.
So here's another question, and I would like to hear from Vanessa, if possible, because I haven't heard from her yet. Are ice molecules different from water molecules? Like, do the molecules actually change? So how do they change? How do they turn into water molecules? So if they're breaking apart, are they like breaking into smaller pieces, or is it the same molecules clumped together and then moving around? So then you're saying that they're the same, it's just whether they're stuck together or not? Or is it your idea that they're different? Same? Okay. So you guys are almost there. Stick with your group, please. You're almost there. So I think you have enough data that you can start writing some results. So write down.
How does the air have like less molecules than the water, I guess?
Okay. And if that's the case, why would that matter?
Because the more molecules you have, the more it can like bump into the others. And the air has less molecules, but it's moving really fast. But it won't be able to like bump into that much, since after it bumps, it'll have to go away, then they come back again. When like the water molecules, they just bump a little, and then they just keep increasing, since there are many of them.
Here, Anna does something unusual to help her students learn to set up criteria for an investigation. Rather than having them identify manipulated, responding, and controlled variables before they are even familiar with the materials, she does this with them in a whole class setting after the activity. This is only done as a strategy, a stepping stone to the more authentic science practice of determining the details of the investigation before it is conducted.
How fast ice melts. Okay. You just told me, Delbert, both our manipulated and our responding variables. They're in that statement. So looking at our manipulated variable, what is the only thing that is different about those two experimental cups that we set up? What's the only thing that's different? Okay, one. What are we measuring? Henry, what are we measuring in this experiment? So what are you keeping track of? What are your numbers that you're getting?
Oh, how fast
How fast it what?
does it melt?
How fast it melts. Nice. Alright, so what are our controlled variables? What are we keeping the same? What is the same between those two cups? Raul, you got some ideas? Okay, hang on. I need everybody to get down to voice level 0. If you're having trouble with this, look at the screen. Your classmates are giving you ideas. Okay, Raul, what you got?
Size of the cup.
The size of the cup is the same. What's another one? Yeah, Curtis.
The size of the ice cube.
Sure. Do we have one ice cube made of Coke and one made of water? No. No, so the size of the ice cube, let's say made of water. There's one other big one that I'm really looking for though. So I'll ask you a question, unless Alana gets it.
The molecule.
So they're all, everything's made of molecules? I'm looking for a really specific one. Yeah. The what? We're using the same timer, that's true. Looking for a really important one, so I'm gonna ask you a question.
The water's temperature.
As
the
Okay, everybody stop, because Victor just told us the really important thing. And Deja, you're right. Thanks for calling me out on that. So, Victor and Deja just said water is the same temperature as the air in the room.
I didn't hear her.
So, what would, that's why I just yelled out. So, hey Henry, do you think it would make a difference if we poured boiling water over that ice cube?
Yeah.
Yeah, right? What if we had a space heater blowing really hot air onto the ice cube? Would that matter?
Yeah.
Yeah, so we said we're taking room temperature, it's all staying the same. If I'm a water molecule and I'm moving at a pretty good speed, and I bump into Bless, am I gonna move him a little bit?
Yeah.
So what if now, instead of just me, Bless is getting hit by several water molecules? Is he gonna get moved a lot or a little? A lot. Okay, but what if Bless is surrounded by a bunch of his friends that are hanging onto him, trying to keep him from getting pushed at all? Do you think it will be harder to make him move or easier? Harder, right? Okay. So your green today is going to be drawing and labeling a picture of the ice in the melting lab. And I'm going to go ahead and say in both cups. Okay, so you need to draw molecules, so maybe draw some zoom-ins to show what's happening. If you choose pink, you're just describing what you saw happen to the ice cube in each cup. Here's some words that you might use. If you are choosing a yellow one, you're explaining why the ice cube in the water melted first. Okay, so we just explained as a class how something melts. So what you need to do if you're doing a yellow is think about what the difference between the air and the water is that surrounds that ice cube and how it changes how fast the molecules are bumped and separated from the ice cube. Here's some ideas of words that you should use if you're doing a yellow. And if you're choosing the purple, you're connecting it back to our big question, our Coke and 7-Up lab. And you're explaining what is happening to the frozen Coke as it melts. Because the pink one is just to describe what you saw happen. And if you're explaining why it happened, you're actually on the yellow. Are you sure? Are you sure?
That's a lot easier.
So I don't want you to do it. It's easy though. I want you to try to push yourself. So I'm actually going to make you do a yellow. In each of these baggies, one of them is going to be filled with cold water from our ice bath. The other one's going to be filled with warm water that we've boiled. It won't be boiled though, it'll be just be warm. These are going to be laid in the bottom of your bin, just like this. Okay, so they'll be nice and sealed off. You're going to lay these paper towels, one paper towel over each baggie. And you've got a little dropper of water. You're going to add just 2 drops of water to each paper towel. So there'll be a big old spot of water on each paper towel. At this time, I would like you to fill out this prediction. So you're writing an if, then, because statement. You're filling in this first blank with hot or cold. and then you're trying to explain why you think the hot one will evaporate faster or why you think the cold one will evaporate faster.
It's ready.
Hi.
Nice. Here it looks like everything's set up. You have it in your bin. So you guys are ready to draw your setup and make your materials list.
Already did it.
So you need to draw your setup.
Okay.
I think it'll evaporate faster.
The hot water one? Why?
Because you know how if it
to
rains
evaporate.
and there's puddles on the ground and it's
Yeah.
sunny,
Yeah.
and the water evaporates faster.
Okay.
And then in cold water, when there's puddles, it takes like a long time.
Okay.
We put this in the freezer.
Which one? Put which one in the freezer?
We put this one in the freezer and dry up like that one.
The paper towel one?
Yeah.
Why?
Because it's freezing the liquid on the paper towel.
So would it be the same process as that?
Yeah.
Okay.
Because the heat evaporates water.
Because heat evaporates water.
Yes. Like the sun.
Like the sun, heat evaporates water. Okay.
Well, it was moving faster than a cold.
What's moving faster?
The speed of the molecule.
Which molecules?
The one with the hot.
Which molecules in the hot?
The one with the paper.
The water
Yeah, the water molecule.
on the paper towel
Yeah,
are what?
are moving faster, and which means when it was moving faster, it automatically.
Okay. Did you guys hear that?
So you see.
Did you understand what Henry said? Because Henry's helping you out.
Because the molecule is moving very fast. The molecule is moving extra fast. And back, number 2 is like in level 1. So which means this has more speed than that. And this is not, it's touching. So which means just spraying. Just making it farther and farther. So which means that's going to take less time than this one.
Are you guys listening? Henry's helping you out.
This is moving very fast, which means that's why the so it evaporated by as when it was moving, it was the water was like it was getting smaller and smaller, and the steam, was
Okay.
Where did that water go?
evaporated into the air.
So it didn't disappear? Is it still there?
Turned into air molecules.
Turned into air molecules? So are they a different kind of molecule now?
Yeah.
than they were? You're saying yes, they're a different kind? Okay. And does your partner think differently? Do you think that the water molecules became air molecules? Are they a different kind of molecule now? Or are you not sure? Go with her? Okay.
So how would a water molecule turn into a different type
Air comes from water.
Okay, so there's two different ideas then, because Alicia, you're suggesting that a water molecule, something changes about it to make it into an air molecule, right? But you're saying that the water stays as a water molecule, but it's different.
Water has molecules, and the sun comes to the water, heat it, and they evaporate it, so then it's water.
So you keep using the word evaporate. What's happening during evaporation to the molecules? So what are they doing that makes them a gas? Okay. Any ideas, Alicia?
They're like just going into the air and like kind of like fitting in, kind of.
This young girl has voiced a powerful theory that particles of water may fit in between particles of air. A moment later, however, she suggests that there is a quote-unquote pulling force that causes evaporation.
Okay, so it's like what molecules are doing the pulling? So the air molecules are like taking the molecules in the water and like pulling them with them into the air. How do they do that? Do they have hands? Do they grab? So they just come down and go and hit it, and then the water molecule goes off into the air?
We leave this video segment with this scene of two learners trying with some success to make sense of events that are both observable and unobservable. Mediating this reasoning is a teacher who, in each segment of this interaction, must draw simultaneously on deep content knowledge, knowledge of how students think, and pedagogical strategies that will move these learners closer to coherent science conceptions.